Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on osmolarity. In this lecture, we will be discussing the terms molarity, osmolarity. We'll do some simple calculations to find out how we can calculate the osmolarity of solutions. We'll identify the terms osmotic pressure. We will see what's the significance of osmolarity in the body. Now let's start off with the basic definitions. What is a mole? What is a mole of a substance? Now, as you must have already studied in high school, a mole contains Avogadro's number of particles, which is 6.023 into 10 to the power 23. So, a mole of a substance has a particular number of particles, and that is Avogadro's number of particles. Now, the gram molecular weight of a substance is the mass of 1 mole. So, if you look at the mass of a mole of a particular compound and you express that in grams, that will be the gram molecular weight, or the molecular weight expressed in grams is the gram molecular weight. So, for example, if you take sodium chloride, we know the molecular weight of sodium is 23, chloride is 35.5. So, the molecular weight of NaCl will be 58.5, and if you take 1 mole of sodium chloride, it will have a weight of 58.5 grams. Now, the term molarity describes the number of moles per liter. So, if you take the given weight and you divide it by the molecular weight, you will find, and if all this is in 1 liter, the given weight in 1 liter by the molecular weight will then give you the molarity of a substance. So, if I take a particular amount of substance and I add it into a solution and I want to know what is the molarity of that solution, I will look at the weight as a fraction of its molecular weight in that 1 liter. So, this is the definition of the term mole and the term molarity. When we look at the different body fluid compartments, the extracellular fluid and intracellular fluid, and we look at the ionic compositions of these different solutions, we realize that this is expressed in millimoles. For example, potassium in the intracellular fluid is expressed as 150 millimoles, or we can say that in the intracellular fluid the concentration of potassium is 150 millimoles per liter. So, this gives us a way of identifying concentrations of different compounds or ions in solutions. Now, let us now describe an experiment, and this is a hypothetical experiment that is described where we take 2 compartments A and B and we fill them with water, and this compartment A is separated from B by a semi-permeable membrane, and we have defined the semi-permeable membrane as a membrane that's going to be permeable only to water. So, ions cannot pass through this membrane, but only water can pass from A to B or B to A. Now, let us say that into this compartment B we add sodium chloride such that the final concentration of sodium chloride in B is 1 mole per liter, or we have 1 molar concentration of sodium chloride in B. What do we expect to happen? This is a more concentrated solution, and so what we would expect to happen is, since this membrane permits flow of water but cannot permit flow of sodium chloride across, water would flow from A to B. If sodium chloride could cross over, if this membrane were permeable to sodium chloride would diffuse here and the concentrations finally would even out. But because this membrane is permeable only to water and not to sodium chloride, water will move from A to B. So, gradually what will we see? We will see that the level in A will drop and the level in B would rise. So, this is the flow of water due to osmosis. How do we prevent this? We can prevent this by applying a pressure on B, and when we apply a particular pressure on B, we will prevent osmosis, and therefore this pressure that is applied is the osmotic pressure. Therefore, osmotic pressure can be simply defined as the pressure that is required to prevent osmosis. What is osmosis? Osmosis is the movement of water molecules from a region where there are higher water molecules or a more dilute solution to a region where there is a lesser number of water molecules or a more concentrated solution. Now, the osmotic pressure is dependent on the number of osmotically active particles in the solution. We talked about the concentration of solution in terms of moles, but when we are talking about osmotic pressure, we need to know how many osmotically active particles are there in the solution. Therefore, we have to introduce the term osmolarity. The number of osmotically active particles in osmoles per liter is the osmolarity. So, if I took this 1 mole of sodium chloride, when sodium chloride goes into solution, it will ionize, and it will ionize into sodium and chloride. So, you will have 1 mole of Na plus, 1 mole of Cl minus, and therefore you will have 2 osmoles per liter from 1 mole per liter of sodium chloride. Similarly, if you take calcium chloride, CaCl2, when it goes into solution, you will have 1 mole of Ca2 plus and 2 moles of Cl minus. So, therefore, you will have 1 plus 2, that is 3 osmoles. Whereas a substance like glucose does not dissociate in solution. So, therefore, 1 mole of glucose will provide 1 osmole. So, it is important to know that 1 mole of a substance that can actually ionize or dissociate in solution will provide a larger osmotic effect. The osmotic pressure is usually represented by the letter pi. How do we measure osmolarity? When you have a certain number of solutes, certain number of solute particles in a solution, this can affect some properties of the solution, such as the depression of freezing point or the elevation of boiling point. Now, we know that the boiling point of pure water is 100 degrees Celsius, and if there are impurities in the water, the boiling point gets elevated, or water boils at a little higher pressure. And if the freezing point of water, of pure water, is 0 degrees Celsius, if we add impurities in water, the water would freeze at a lower temperature. Now, this elevation of the boiling point or this depression of the freezing point is dependent on the number of particles that are there in the solution. It does not depend on the size of the particles, it does not depend on the mass of the particles, but it depends only on the number of particles. And those properties which are dependent on the number of particles are called colligative properties. So, elevation of boiling point or depression of freezing point are colligative properties, and by looking at the elevation of boiling point, we can actually measure the osmolarities. And an instrument that measures osmolarity is called an osmometer, and common osmometers that measure the osmolarities of a solution look at how much the boiling point is elevated or how much the freezing point is depressed, and therefore they are able to calculate the osmolarity. So, we have said that when you have a certain osmolarity, that causes a particular osmotic pressure, and the osmotic pressure can be defined as the pressure that is required to prevent or resist osmosis. Now, how do we measure this osmotic pressure? You will intuitively understand that the more the osmolarity, the more will be the osmotic pressure, and the relationship between them is given by an equation. That equation is called the Vant Hoff's law, which says pi is equal to phi IC into RT, and this gives us the relationship between the osmolarity and the osmotic pressure. Let's look at this in a little more detail. So, in this equation, pi is the osmotic pressure, R is the gas constant, and T is the absolute temperature or the temperature in Kelvin. Now, this term phi IC represents the osmolarity. So, we can see that the osmotic pressure is directly proportional to the osmolarity. Now, why do we say that phi IC represents the osmolarity? Let's break this up a little more. C is the concentration of what you add in moles. So if we add 1 mole of sodium chloride, C will be 1. I will be the number of ions produced in solution. So for example, for sodium chloride, C will be 1 because we added 1 mole of it, and sodium chloride produces 2 ions in solution. So I will be 2. Now phi will be the osmotic coefficient, which describes how much the solution deviates from normal. So when we add 1 mole of sodium chloride, we expect it to fully dissociate and to produce 2 osmoles, but in reality that may not be so. It may be 99% dissociated. So phi tells us what is the total amount. Is the dissociation complete or is it incomplete? So that's the osmotic coefficient. So by multiplying all these, the molar concentration into the number of ions produced in solution to the osmotic coefficient. Now for most dilute solutions, the osmotic coefficient is taken as 1 and we can assume that it is fully dissociated. So this term phi IC will give us the osmolarity. So this relationship between the osmotic or the osmolarity and the osmotic pressure is given by this equation, which is called Vant Hoff's law. Let us now pause for a moment and do a problem. Let us try to calculate the osmolarity of a solution which contains a 0.9 gram percent of sodium chloride, given that the molecular weight of sodium chloride is 58.5. So in this problem, we have been given a 0.9% solution of sodium chloride and we've been asked to find out its osmolarity. Now we've also been given that the molecular weight of sodium chloride is 58.5. Now what do we mean by a percentage solution? When we talk about a percentage solution, we mean how much of solute is there per 100 ml of the solvent. So a 0.9% solution means 0.9 grams per 100 ml. Now the easiest thing to do is to convert this into a liter. That's equal to 9 grams per 1000 ml or 9 grams per liter. Now we know that molarity is the given weight, let's say x divided by the molecular weight. Now here the given weight is 9 grams per liter divided by the molecular weight is 58.5. So if you do these calculations, you'll do 9 divided by 58.5 is equal to 0.1538, or this is 0.1538 moles per liter, or we will convert it to millimoles. That's 153.8 millimoles per liter. So when we add 0.9 grams per 100 ml, we get a solution that has a molarity of 153.8 millimoles per liter. But now we know that when we add 1 mole of NaCl, this will give us 1 mole of Na plus, and it will also give us 1 mole of Cl minus. So when we calculate the total number of osmotically active particles, we will have 2 not moles but 2 osmoles. So we will get 2 osmoles of osmotically active particles. So 153.8 millimoles per liter of sodium chloride will correspond to 153.8 into 2, that's equal to 307.6 milliosmoles per liter, or we can roughly say about 308 milliosmoles per liter. This is our osmolarity. Now this 0.9 gram percent solution of sodium chloride is sometimes called normal saline, and so normal saline has an osmolarity of about 308 milliosmoles per liter, which is very close to the osmolarity of plasma. So in this problem, we have been told that the amount of glucose or fructose in a soft drink is 12 grams per 100 ml, and we've been asked to calculate the osmolarity, and it is assumed that the carbohydrate is glucose or fructose and its molecular weight is 180. So let's begin. So we know that 12 grams per 100 ml is the amount that is added, and we know that we can now convert this into 1 liter. So that's 12 grams per 100 ml, that's equal to 120 grams per 1000 ml. Now we know that the molarity is equal to the given weight x divided by the molecular weight. So here the given weight is 120 grams and the molecular weight is 180. So the molarity is equal to 0.667 moles per liter. Now let's convert this into millimoles. That's equal to 667 millimoles per liter. Now, since this carbohydrate, either glucose or fructose, when put into water does not dissociate, 1 millimole or 667 millimoles will cause 667 milliosmoles. So 1 mole will cause 1 osmole of osmotic pressure. So the osmolarity will be 667 milliosmoles per liter. So if you take 12 grams per 100 ml of glucose or 12 grams per 100 ml of sucrose, the resultant osmolarity will be a hyperosmolar solution which will have an osmolarity of 667 milliosmoles per liter. Now, how do you measure the flow due to an osmotic pressure? The flow through an osmotic pressure is given by this equation: J is equal to L into delta pi, where J is the flux or the total flow, L is the hydraulic conductivity, and delta pi is the osmotic pressure gradient or the osmotic pressure difference between the two compartments. Now let's go back to the illustration that we used before. We had used this illustration where we had two compartments A and B. There was a particular solute in compartment B with a particular osmolarity, and that caused an osmotic pressure pi. Now we said delta pi will be the difference in osmotic pressure between the two compartments. So delta pi will actually be pi because the osmotic pressure in this compartment would be 0. So therefore, because there was an osmolarity leading to an osmotic pressure pi, there would be movement of water from A to B. Now this membrane, which we said was permeable to water, we could say that in another way by saying that this membrane has a hydraulic conductivity or permits the passage of water with a conductivity L. Now we know that in a cell, for example, the cell membrane is a lipid bilayer, and this lipid bilayer is impermeable to water. So the hydraulic conductivity of a lipid bilayer is very low. So how does water cross the cell membrane? Water crosses the cell membrane by specialized water channels which are called aquaporins. So aquaporins, if this were the cell membrane, aquaporins inside in the cell membrane would contribute to the hydraulic conductivity of the membrane. There are a lot of other ion channels like sodium channels, potassium channels, and when those channels open, there's also a passageway for water. So this hydraulic conductivity, or when we said the membrane was permeable to water, we are actually saying that there is a hydraulic conductivity for water, and that is determined by the various ion channels or also by aquaporins. What is the osmolarity of plasma? The osmolarity of plasma is about 280 to 300 milliosmoles per liter. What are the ions that contribute to this osmolarity? Now we know that in the ECF or in plasma you have a predominance of sodium and you have a predominance of chloride. So sodium, chloride and bicarbonate themselves contribute to about 270 milliosmoles of the total osmolarity. Plasma proteins contribute only to about 2 milliosmoles per liter. However, when we discuss edema, we will see that even though plasma proteins contribute only to about 2 milliosmoles, this contributes to the colloidal osmotic pressure, whereas all the ions contribute to what is called the crystalloid osmotic pressure of plasma. Glucose contributes about 5 milliosmoles per liter and urea about 5 milliosmoles per liter. So these are the various substances that contribute to the osmolarity of plasma. Now let us use another illustration. Let us assume that we have 3 different beakers, and into each of these 3 different beakers we are going to drop a cell. Let us say it's an RBC. Now the first beaker contains an osmolarity of 280 milliosmoles per liter, which is very similar to that of plasma. So we will say it is iso-osmotic with plasma, or this ICF also will have an osmolarity of about 280. So this beaker and this cell are iso-osmotic. In this beaker, the osmolarity of this beaker is 400 milliosmoles per liter, which is greater than the ICF. So we say this is hyperosmotic, or when one solution is more osmotic than another, we say that it is hyperosmotic. And in this solution, we have an osmolarity of 150 milliosmoles per liter. So we will say that this is a hypoosmotic solution. Now what we are going to do is we are going to drop these cells into each of these solutions and see what is the effect. Now when we drop a cell into an iso-osmotic solution, there is no change. The cell's volume does not change because the osmolarities within the cell and outside the cell are the same. When we drop a cell into a solution which is hyperosmolar, what happens is the fluid from the cell will leave and go into the external solution, and therefore the cell will slowly shrink, or there will be crenation of the RBCs. So when a cell is put into a hyperosmolar solution, there will be cell shrinkage. Now if we put a cell into a hypoosmotic solution, water from outside the cell will enter the cell, and there will be a cell swelling, or there will be an increase in volume, and in certain cases the cell swelling may be so large that the cell could even rupture. Now let us go back to the experiment that we discussed, where we have 2 containers A and B separated by a membrane with a hydraulic conductivity L, and we said that the flow or the flux will be equal to the hydraulic conductivity into the delta pi. Now this was true assuming that this particle was completely isolated, and this particle and the membrane was completely impermeable to this particle. However, what would happen if this particle also could cross the membrane? If this particle can also cross the membrane, then the osmotic effect that this particle will have would be much less, because a part of it would move into the other compartment, and therefore the total osmotic effect would be less. It would not draw in so much water. So to explain the effect of a permeable compound, or when a compound is permeable for that particular membrane, we need to introduce another coefficient called the reflection coefficient. So the reflection coefficient actually talks about how permeable is that compound for this particular membrane, because very rarely do we have a compound that's absolutely on one particular compartment and cannot permeate through the membrane. There may be a small amount of permeability that's present. So what is this reflection coefficient? When we discussed the flux or the flow due to osmolarity, we had initially said that J is equal to L into delta pi, where L was the hydraulic conductivity and delta pi was the osmotic pressure gradient, and J was the flux. Now we are going to introduce the term reflection coefficient, or sigma, here into this equation, where we talk about the total flux. This reflection coefficient describes the osmotic flow created by the solute as a fraction of the total theoretical osmotic flow. So if I put this solute into a compartment and it had a particular osmotic effect, that is a theoretical maximum osmotic effect. But if this particle diffused through the membrane, it would have a much lower osmotic effect, and the ratio, the fraction of this low osmotic effect to the total osmotic effect is the reflection coefficient. So this is a number varying from 0 to 1. So if the membrane is fully impermeable for that particular compound, then the reflection coefficient is 1. If the membrane is absolutely permeable or it's fully permeable, then basically the reflection coefficient will be 0, or the molecule will not have any osmotic effect because it was in one particular compartment, it was fully permeable, it moved to the other compartment, and therefore there will be no osmotic effect. Now this reflection coefficient is represented by the symbol sigma. So let us now see what happens when we put in a cell into an isoosmotic solution. However, this solution consists of a particle whose reflection coefficient is less than 1, or this particle can actually cross the cell membrane. Let's see what happens. So we put this cell inside, and we know that now, since the reflection coefficient is less than 1, this particle can enter the cell. Now what happens is the osmolarity inside the cell is more, so there will be water movement into the cell, and therefore the cell will swell up. So this solution, even though it was theoretically or calculated to be isoosmotic, in effect it behaved like a hypoosmotic solution. By our calculations, this solution should have been isoosmotic. But because the reflection coefficient was less than 1 and this molecule which created the osmolarity could permeate the membrane of the cell, this effectively behaved like a hypoosmotic solution. So therefore, we need to introduce the term tonicity. And tonicity describes how a solute causes osmosis across the cell membrane. So when we talk about different fluids which are used for the body, we use the term tonicity, and basically this means what is the net movement of water into a cell or out of a cell when a cell is placed in that solution. How does this solute cause osmosis across the cell membrane? In an isotonic solution, there is no movement of water, no net movement of water either in or out of the cell. In a hypotonic solution, water enters the cell and the cell will have cell swelling, whereas in a hypertonic solution, water exits the cell and there will be cell shrinkage. So now let us look at the same experiment that we saw again, but this time instead of saying isoosmotic, I'm going to say isotonic. So when a cell is put into an isotonic solution, there is no volume change. When a cell is put into a hypertonic solution, water will exit the cell and there will be cell shrinkage. And when a cell is put into a hypotonic solution, water will enter the cell, there will be cell swelling and the cell may even rupture. Now, we said that the osmolarity of plasma is about 280 to 300 milliosmoles per liter. How does the body recognize what the osmolarity is? The body has certain osmoreceptors which recognize the osmolarity of the plasma, and these osmoreceptors are present in the OVLT, that's the organum vasculosum of the lamina terminalis, which is in the brain but outside the blood-brain barrier. This can recognize a 1 or 2% change in osmolarity. So when there is an increased osmolarity, it will stimulate the hormone ADH, or antidiuretic hormone, from the posterior pituitary, and when there is hyperosmolarity, this will also stimulate thirst, or we feel more thirsty and we feel like drinking water to bring down the osmolarity. So this flowchart shows you the effect of an increased osmolarity. When there is an increase in osmolarity, this is picked up by the osmoreceptors, which causes an increased ADH secretion from the posterior pituitary, causing increased water reabsorption, therefore causing a decrease in osmolarity and bringing the osmolarity back to normal. This increase in osmolarity will also stimulate the thirst mechanisms in the hypothalamus, causing an increased intake of water, therefore there's an increased blood volume, therefore bringing the osmolarity back to normal value. So this is the way in which the body has a defense of osmolarity. When the osmolarity increases, the body can decrease the osmolarity. Now, what are conditions that the osmolarity increase? Let's say it's a very hot day and we have been exercising, we have lost a lot of water through sweat. The osmolarity of the blood or the osmolarity of plasma can increase. Let us say that a person has severe burns and there is a loss of water through the burns, then a person can get dehydrated and the osmolarity can increase. So in all those conditions when there is an increase in osmolarity, these are the mechanisms by which the body is able to bring the osmolarity back to normal. Another test that is done is the osmotic fragility test, where we look at the ability of an RBC to resist an osmotic challenge. So that is done by taking an RBC and putting it into solutions of varying osmolarity and seeing at which hypoosmolar solution there is lysis of an RBC. So this fragility is increased in conditions such as hereditary spherocytosis and is a test that is used to diagnose this condition. So in conclusion, we have discussed the terms molarity, osmolarity, the relationship between molarity and osmolarity. We've talked about what happens when we put a cell into an isoosmotic, hypoosmotic and hyperosmotic solution. We've talked about permeability of the solute for a membrane and the reflection coefficient, and therefore the importance of isotonicity and having isotonic solutions. We've also looked at the way in which the body is able to identify osmolarity, that is the osmoreceptors, and the way in which the body is able to correct the osmolarity of plasma when there is a change. Thank you.